Alright, walk-in freezer, something's not right, it's not obvious. The compressor is super hot, hotter than just the crankcase heater would make it. The high pressure line is just cool. When you come over here and look at the liquid receiver, you can tell it's got liquid in it that's boiling. It's also sweating. So presumably the compressor is actually cut out on thermal overload. So I shut the system off, we're gonna let it cool down. I'm gonna check the capacitors, make sure that the run capacitor is good, make sure the start capacitor is good, and look over all the wiring, make sure the wiring is set up properly. This capacitor was actually blown, but it was replaced a few days ago by my dad. And he said that, you know, it took right off after he replaced the capacitor and he wasn't really worried about it after that. However, when he came back the other day, it was hot, so he told me I needed to come look at it and see if I could figure out why it's still running hot. So I tested the start capacitor right here and the run capacitor, and both of those seem to be working fine. So I think we're going to try changing out the actual relay. If you look at how these are set up, they're responsible for adding this capacitor in to the circuit directly, basically jumpering onto where the run capacitor is tied into the circuit. So when the compressor starts and the inrush current is felt by this, it snaps a coil in, which applies this capacitor to the circuit for just a moment to get it started, and then it disconnects again. If this is left in the circuit, it can cause problems. If it's not coming into the circuit, it can also cause problems. So we might have some issue with that, which is causing the compressor to intermittently not start and then get really hot while it's sitting there. Between 5 and 2, you can see that little coil symbol. This is 2, this is 1. So between here and here, we should get a reading in ohms, because we should be sensing that coil. So 6.63 kiloohms. So this obviously has a coil in it, and the coil is good. Now we'll test on the old one and see if we're getting any kiloohm reading where that coil is. Oh, 7.2 kiloohms. So it actually seems like it's good. However, we might pop the cover off of it and just look and see if the contacts are welded or something. Okay, so here's the inside of the contact. You can see it is actually quite dirty. So I'm just gonna see if these contacts are welded when I pull on this. Hard to say, I don't really think it was welded. Those contacts really don't look very good though, so I think we are going to still just replace it and leave it replaced. So now I'm cooling it down with water so that hopefully the thermal limit will close again. So I've returned, and now we no longer have an open winding, but we actually have continuity here. 0.7, we'll call it 1, plus 2. So this should be about 3.5 then. Yep, 3.6. So the two low values should equal the highest value. So the compressor is ohming out good. So we'll throw the wires back on and then start it up again. Nice. So compressor started fine. Drawing 14 amps. Nothing seems weird. Put it in a defrost and it is short cycling, so that's definitely the problem. Kicking in at 20. Kicking out at 8. So we might have a valve like the liquid line solenoid and see if it's bleeding past it. It has an internal leak. Can you hear that? It's so sad. I've never actually seen that happen, but there's an internal leak on this compressor, where it's either the relief valve in the compressor or the reeds themselves. Something is opening up a little bit, causing it to short cycle. So the top of the compressor is quite hot. Suction line is cool coming in, but I think the relief valve is like leaking. So it's spraying hot compressed gas right back up into the compressor here. To prove this, we're going to close this liquid line, which will cause it to evaporate all the liquid out of this line going up there and condense it into here. This should have space to hold the entire refrigerant charge. Obviously it'll be a little bit more because it will have to hold that capacity that was normally in that line there, but this will prove our theory. By just closing this valve, it'll be putting it in a pump down state. And if it still short cycles with this pumped in the pump down position, then we know it's not the liquid line solenoid or something with the evaporator. We'll know that it's just this. Alright, so it did finally shut off. This got sweaty. Yeah, you can hear it. It's leaking past. Sad. Because it still works, you know? It's just so that's why it destroyed the start components, because it could never pump down. Yeah, I don't know if it's weak reeds or if it's relief valve, but we're gonna need a new compressor. So we've returned, we're cutting out the old system here, and we're going to put in a new, different style of condenser. When we were trying to source parts, that particular compressor is like $3,500 now, because evidently Copeland is trying to phase out their old reciprocal compressors, so they just jacked the prices on everything to the point where no one can afford to fix their old condensers that have reciprocal compressors. So we were told that we needed to replace the condenser, and this is the new condenser, which is like the same price as the old unit's just compressor. So that's what we're going to do here. This was actually a really easy system to replace the entire condenser on, because we only had to supply power to it, being a pump down system, and we didn't have to change anything with the thermostat or with the defrost timer and how that stuff is set up, since it's just opening and closing the solenoid valve. So here Simeon is brazing it up. We had to use some copper to steel braze as well. So there it is, all installed. I think it looks pretty nice. We added that wood support just to keep vibration down with the line set. The line set is also hung over there. Oh yeah, I think it looks good.